Welcome to this custom-tailored deep dive. We're incredibly excited to have you with us today because we're heading straight onto the modern manufacturing floor.
Yeah, we are.
We're exploring this highly specific, incredibly high-stakes environment where a fraction of a second literally translates into thousands of dollars in profit or loss.
It's intense.
It really is. Today, we're looking at a piece of machinery known as a tapping center. It's the absolute, undisputed king of milling aluminum. But, and this is the vital kicker we're going to explore, it's also a machine that will practically destroy itself if you try to use it on heavy steel.
Right, and it's the perfect case study for you if you've ever been curious about the intersection of physics and business.
Exactly.
Because you see these mass manufacturing operations run by incredibly smart people, yet they're actively bleeding money on the factory floor.
Just throwing it away.
Literally.
Yeah.
And simply because they mismatch the mechanical capability of a machine with the actual physical properties of the material they're trying to cut, it happens far more often than you'd think.
Okay, let's unpack this. Because for you, the learner listening right now, this isn't just a technical breakdown of factory equipment.
Not at all.
It's a story about the uncompromising physics of materials. It's a masterclass in the value of hyper-specialization in modern manufacturing. And crucially, it's about how to avoid making catastrophic, wildly expensive capital mistakes.
Exactly. When you're running a mass production facility, turning out hundreds of thousands of laptop chassis or smartphone bodies or automotive engine components, you just can't afford a single inefficiency.
Right, the scale is just too big.
Yeah, you have to understand exactly how the metal behaves at a microscopic level and exactly what forces your machine is capable of applying to it. If
Yeah.
those two things don't align perfectly, your profit margins just vanish.
Poof, gone. So let's start with the first major hurdle of milling, which is aluminum.
Okay.
People generally think of aluminum as a pretty forgiving metal, right? I mean, it's lightweight, it's malleable, it's everywhere. But cutting it presents a really unique challenge. Our source describes it brilliantly. Cutting soft, sticky aluminum slowly is basically like trying to cut through a thick wad of chewing gum.
That is a highly accurate way to visualize the mechanics at play there. Aluminum is a ductile metal.
Meaning it bends and stretches.
Right. It's soft, but more importantly, it's sticky. If you take a standard heavy-duty milling machine and try to cut aluminum at a relatively slow spindle speed, the metal doesn't shear away in clean chips.
Like you'd want it to.
Exactly. Instead, the heat and friction cause the aluminum to essentially micro-weld itself right to the cutting tool.
Huh.
The industry term for this is a built-up edge.
A built-up edge. So the waste material is literally fusing onto the end mill that's trying to cut it?
Yeah, it just globs on.
That sounds like a really quick way to ruin a cutting tool.
Oh, it ruins the tool and it ruins the part. When that built-up edge forms, the sharp flutes of the cutting tool are covered in gummy aluminum. You're no longer slicing the metal.
You're just kind of mashing it.
You're bludgeoning it. You're tearing and ripping the aluminum apart. And for a shop owner, this is a worst-case scenario. It leaves a rough, torn, cloudy surface finish on the part.
And I imagine that translates directly to a massive bottleneck on the production line.
Oh, massive.
Because if the machine leaves a terrible finish, you now have to pay someone to stand there and manually polish those parts to meet your quality standards.
Right.
You've just added a huge labor-intensive step to your workflow simply because you cut the metal too slowly.
Precisely. You're bleeding time and labor costs.
Which brings us to the tapping center's absolute superpower. This specific machine solves the gum problem with raw, staggering speed.
Unbelievable speed.
These tapping center spindles are spinning at 20,000 RPM, with some top-tier models hitting 30,000 RPM.
Yeah.
But wait, if you're spinning a piece of carbide at 30,000 RPM inside solid metal, my first thought is friction. Wouldn't that generate so much heat that you'd just melt the tool entirely?
You would think so, but what's fascinating here is how that extreme speed fundamentally alters the physics of the cut.
How so?
At 30,000 RPM, you're moving so incredibly fast that the heat actually doesn't have time to transfer into the tool or the workpiece. Almost all the heat generated by the friction goes directly into the metal chip that you just carved away.
Ah, so the waste material basically absorbs the thermal shock.
Exactly. And because the tool is slicing so fast, the soft aluminum simply doesn't have the time or the sustained friction to micro-weld to the blade.
So no gum.
No gum. There's
Wow.
no built-up edge. It slices cleanly, leaving a brilliant, mirror-like finish straight off the machine. You completely eradicate that manual polishing step.
That is wild, and that explains why chip ejection is such a big deal with these machines, doesn't it?
It's critical.
Because of those high speeds, centrifugal force acts almost like a jet engine. It violently and instantly ejects those hot metal chips away from the cutting zone.
That ejection is non-negotiable. If you're cutting at 30,000 RPM and the chips linger in the cutting area, the tool will recut its own waste.
Which is
very bad. Those flying superheated chips will either scratch that perfect mirror finish you just achieved, or they'll fuse into a molten mess around the spindle.
ruining the part anyway.
Exactly. By using centrifugal force to launch those chips out of the way, the machine protects both the part and the tool. It's a methodology known as the light and fast strategy. You take very shallow cuts, but you feed the tool at blistering speeds.
And it isn't just about surface finish either. The mechanical precision is incredible. When you look at the data for small workpieces, specifically components under 50 millimeters, this light and fast strategy is virtually the only way to hold tight tolerances.
Absolutely. With parts under 50 millimeters, any lateral vibration will chatter the part right out of spec.
It'll just vibrate right off the table.
Pretty much. So tapping centers use specialized electro spindles designed for stability. They have a runout of less than a micrometer.
Run out being the physical wobble of the spinning tool, right? Meaning it's perfectly centered.
Correct. A runout of under a micrometer means the wobble is practically zero. You have total rigidity, ensuring that even when the machine is screaming at 30,000 RPM, the tooltip is dead stable.
Here's where it gets really interesting. Because if we look at everything we just covered, tapping centers sound like the ultimate manufacturing cheat code.
They do.
They're unbelievably fast, they leave a flawless finish, they have microscopic precision. So why do they fail so spectacularly the moment you try to use them on a block of heavy steel?
Because shop owners often confuse speed with muscle.
Speed with muscle.
Yeah, it's the classic difference between horsepower and torque. We established that aluminum is soft. On the Brinell hardness scale, which measures a material's resistance to indentation, aluminum usually sits around 50 to 1 in 50.
Okay.
Steel, depending on the alloy, has a Brinell hardness of 200 to over 400.
Yeah.
It has massive shear strength.
So it's a completely different physical environment. You can't just spin a tool at 30,000 RPM and expect it to melt through solid steel.
If you try that, the tool will instantly shatter. To shear through heavy alloy steel, you actually need very low speeds, usually well under 6,000 RPM. But at those low speeds, you need immense twisting force. You need torque. And this exposes the structural compromise of a tapping center.
Right, the direct drive spindle. Tapping centers use electrospindles where the motor is connected directly to the cutting tool without any gears in between.
Yes.
The entire architecture of the machine is optimized to hit maximum RPM as fast as possible. But to achieve that, they've entirely sacrificed low-end torque.
They traded all their structural muscle for pure rotational speed. Trying to cut heavy alloy steel with a direct drive tapping center is exactly like trying to tow a 10,000-pound trailer with a Formula One race car.
That is a brutal mental image.
It really paints the picture.
You've got this highly tuned, incredibly fast engine screaming at the red line, but it's hitched to a massive, immovable weight. The car isn't going anywhere. The engine is just going to smoke and burn itself out under the load.
And that's precisely the sequence of events on a factory floor when someone ignores the material physics. An operator tries to cut a deep pocket into stainless steel using a direct drive spindle.
Okay.
The physical resistance from the steel is overwhelming. The motor simply doesn't have the torsional force to push the cutter through the metal.
And the failure cascade from that is violent. You get massive resistance and the machine starts chattering.
Yes.
This aggressive, destructive vibration that shakes the whole frame. The tool starts slipping or the spindle simply stalls out in the cut. And if the spindle stops rotating while the machine's axes are still trying to push it forward through the steel,
The tool snaps. The spindle bearings get crushed.
Mm.
The motor overloads.
it's a disaster.
And suddenly the shop owner isn't just looking at a broken $20 end mill. They're looking at a destroyed $20,000 spindle and a week of machine downtime. That's a financial catastrophe for a job shop.
It's a huge risk to take just to run one machine.
It is. If you're cutting heavy steel, you cannot use a direct drive sports car. We absolutely need a machine with a geared transmission or a heavy-duty belt drive that multiplies the torque.
You need the muscle.
You need a heavy, slow, rigid approach. You need a heavy-duty truck.
Which pivots us perfectly to the next major concept in our deep dive, which is optimizing the time the machine spends doing absolutely nothing.
Oh, this is huge.
We've talked about the physics of cutting, but what about non-cutting time?
Non-cutting time is the silent killer of factory efficiency. It's the wasted fractions of a second. A machine spends just spinning its spindle up to the target RPM, braking to a stop, or physically moving through empty air to get to the next hole location.
Right, because if you're a hobbyist making a single part in your garage, a few seconds here or there is totally irrelevant.
Doesn't matter at all.
But for a business mass-producing complex components, those tiny gaps of dead time accumulate into hundreds of hours of lost production over a year.
Returning to our vehicle analogy, a standard heavy-duty mill, the truck takes time to accelerate. It has heavy cast iron components, massive ball screws, and a heavy spindle.
A lot of inertia.
Exactly. It takes time to get that mass moving, and it takes time to break it. A tapping center, however, is built with ultra-light moving parts and highly responsive servo motors.
The acceleration stats on these things are honestly hard to fathom. A modern tapping center can ramp its spindle from 0 to 12,000 RPM in just 0.6 seconds.
Less than a second.
And when the machine needs to physically travel across the workpiece, it can accelerate to a moving speed of 48 meters per minute in a blistering 0.18 seconds.
It's practically teleporting. That rapid stop-and-go capability is revolutionary for operations that involve heavy drilling and tapping.
Let's clarify tapping for a second, too, because it's literally the name of the machine. Tapping is the process of cutting internal threads into a drilled hole so you can screw a bolt into it later.
Right.
And rigid tapping is notoriously difficult for standard machines.
It is, because rigid tapping requires perfect synchronization. The spindle's rotation and its downward feed rate have to be locked together perfectly to match the pitch of the thread.
They have to move as one?
Yes. When the tap reaches the bottom of the hole, the spindle have to brake instantly, reverse direction, and back out at the exact same synchronized rate. If the motor lags or overshoots by even a fraction of a millimeter, the tap snaps off inside the hole, and the part is ruined.
But because the tapping center uses those ultralight components and highly responsive servos, there's no lag. It brakes and reverses in milliseconds.
Flawlessly.
The real-world impact of eradicating all that non-cutting lag is profound. Take a complex aluminum casing that needs dozens of threaded holes. On a standard heavy truck-style machine, the sheer amount of time spent spinning up, slowing down, and moving between holes might make that job take 4 hours.
But put that exact same part into a tapping center, leveraging its 0.6-second spin-ups and 0.18-second rapid movements, and that 4-hour job often drops to 1.8 hours.
That is insane.
That's a 55% reduction in cycle time, purely from eliminating non-cutting delays.
A 55% jump in throughput without even changing the actual cutting tools. That's the difference between a shop scraping by on thin margins and a shop completely dominating its competitors.
If we connect this to the bigger picture, there's one more massive mechanical bottleneck in CNC machining that the tapping center completely redesigns, and it's arguably the most important one for high-volume production.
The tool changes.
Yes.
Picture this for a moment. You're watching a machine work on a complex aerospace part. It needs a spot drill, then a deep drill, then a tack, then a roughing end mill, then a finishing end mill, maybe 20 different tools in total.
Right.
A standard vertical machining center uses a heavy cam-driven mechanical arm or an umbrella-style carousel to physically pull the old tool out of the spindle and insert the new one.
And those standard tool changers take about 2 to 4 seconds to execute a swap. Now, 3 seconds doesn't sound like a long time.
No, not out loud.
But when you're standing at the machine, watching it swap tools 20 times 1, 2, 3, the machine is just sitting there, not making money. It feels agonizingly slow.
It's just dead time. So how does the tapping center solve this? I know they use something called a flying saucer magazine, which sounds like total sci-fi, but what is it mechanically?
The Flying Saucer magazine is a highly compact circular tool carousel mounted directly adjacent to the spindle head. Instead of a complex mechanical arm swinging back and forth, the spindle simply raises up, the saucer clicks one step over, and the spindle drops onto the new tool.
So simple.
But the real secret isn't just the mechanism, it's the weight. Tapping centers use a specific tooling standard called BT30.
Right, BT30. Compared to the heavy BT40 or CT40 tools used in standard mills, BT30 tapers are much smaller and significantly lighter.
Exactly. Less mass equals less inertia. Because the tools are lighter and the magazine is compact, the servos can whip that carousel around with incredible violence and precision.
The speed metrics here are staggering. A flying saucer magazine can execute a tool-to-tool swap, meaning the physical exchange of the tools, in zero point 0.6 to 1.2 seconds.
Blistering.
And the chip-to-chip time, meaning the total time from when the first tool stops cutting the metal to when the second tool starts cutting the metal, is a mere 1.6 seconds.
This raises an important question about scale, particularly regarding CapEx or capital expenditures. Let's do the math on the factory floor.
Okay, let's hear it.
If you save just 2 seconds per tool change compared to a traditional mill, and your part requires 20 tool changes, you save 40 seconds of dead time per part.
40 seconds saved every single time the doors open.
Now, multiply those 40 seconds across a production run of 50,000 parts over a year. That time savings is massive.
It really is.
But here is the real business insight. Saving that much time means your factory is producing significantly more product every week without increasing overhead. It means you can take on a massive new contract for a different client without having to spend $150,000 to buy and install an additional machine. You've effectively scaled your factory's capacity just by changing the tool swap mechanism.
You're getting the output of 2 machines out of the footprint of 1.
Precisely. That 30% to 50% speed advantage in tool changes translates directly to scaled revenue. But again, it all hinges on the fact that you're cutting aluminum or plastic.
The soft stuff.
Right. The moment you introduce heavy steel, all those lightweight BT30 tools and ultra-fast servos become a liability rather than an asset.
So what does this all mean? We've journeyed through the gum-like stickiness of ductile aluminum, the thermal dynamics of 30,000 RPM chip ejection, the catastrophic race car towing a trailer reality of milling heavy steel, the eradication of non-cutting time, and the incredible CapEx advantages of the flying saucer tool changer.
We covered a lot of ground.
We did. And it's wildly apparent that tapping centers utterly dominate aluminum mass production through sheer unadulterated speed. Speed in rotation, speed in acceleration, and speed in tooling swaps. But the ultimate takeaway is that extracting that kind of elite performance requires deeply respecting the physical limits of the materials you're working with.
That's the core lesson for you to apply, whether you're in manufacturing or any other field. True efficiency isn't just about buying the fastest, most expensive system available. It's about meticulously matching the exact right capability to the exact right environment.
Form-fitting to function.
Exactly. A Formula One car is an engineering marvel on a paved track, but it's useless for plowing a field. A tapping center is a miracle worker for soft metals, but it will literally tear itself apart against heavy steel. Hyper-specialization demands hyper-awareness of your environment.
Which leaves us with a really fascinating thought for you to chew on long after we wrap up today. If extreme speed, lightweight components, and highly specialized designs make tapping centers absolutely perfect for aluminum but catastrophic for steel, what other processes, teams, or software systems in our modern world are secretly relying on hyper-specialized race cars that would instantly break down if we asked them to pull a slightly different load? Are there areas in your own workflow that are specialized to the point of fragility? Something to mull over as you go about your day. Thank you for joining us on this deep dive into the hidden high-speed world of modern manufacturing.